Assalamualaikum warahmatullahi wabarakatuh. We are from BTO 3283 Formation Evaluation. This is our presentation about our project about log interpretation. This is our group members. Me, Muhammad Akmal Shoki bin Mak Fauzan, Wan Muhammad Afif Hilmi bin Wan Muhammad Nur, Muhammad Sairul bin Sanusi, and Nurliana Afikah. Here is the discussion outline for our today's presentation. The project abstract, brief introduction, data and methodology, log analysis and interpretation, result and conclusion. For the abstract, fractal analysis of wireline log in Bokpara oil field characterized hydrocarbon HC and non-hydrocarbon NHC zone. Well log reaction including SP, GR, LLD, LLS, MSFL, NPHI and RHOB are adjusted to SAM boundaries using Risklev locales RS and power spectral density PSD techniques. Analysis of fire wells indicates higher HPSD values in HC zone, emphasizing scaling pattern in potential zone. Fractal analysis applied to wireline log data of various HC and NHC zones highlight HRS with higher values in HC zone for all reactions. This approach mitigates errors in hydrocarbon zone identification, enhancing precision in oil field characterization. Oil exploration in Bokpara Asam Arakan Basin demands precise hydrocarbon identification. Traditional seismic techniques and wellbore analysis are enhanced in the study. Introducing fractal geometry (RS) and PSD analysis for well log evaluation. Various well logs representing geological features are analyzed, focusing on hydrocarbon-rich zone over 100 meters with layered structure. The study aims for comprehensive fractal characterization to understand spatial heterogeneity by examining the fractal nature of well log data. Researchers aim to uncover patterns missed by traditional methods. This innovative perspective provides valuable insight into Bokpara complexity in the context of India's energy resources. The study's importance lies in increasing oil exploration efficiency through unconventional analytical tools. Fractal analysis contributes to a holistic understanding of subsurface formation, revolutionizing exploration in evolving oil gas industry.
Assalamualaikum. My name is Nurliana Afika binti Muhammad Isamuddin with metric ID TH21027. I'm going to continue the presentation with the methodology. The first one, methodology of spontaneous potential SP log. SP curve logging, continuous recording of electrical potential difference between movable and surface electrodes. They located adjacent uh, to shale and deviates from shale baseline. The shape and the departure from shale baseline is crucial for the features. So SP log curve deflections can be determined by the deflects to left and or to the right of the shale baseline. The deflections can be negative or positive depending on the salinities of the zone. The direction depends on formation water and mud filtrate salinity. Next, the methodology of resistivity log. Resistivity log is basically electrical well logs that measure the resistivity of formation. Resistivity is typically recorded in ohm meter and it is displayed on the second track. The characterized rock or sediment in a borehole by measuring its electrical resistivity. There are three depths of resistivity that can be logged, which are shallow, medium, and deep. The interpretation is used to infer information about formation porosity, water saturation, and hydrocarbon present. Um, it is also measured using four electrical probes to eliminate contact slits of resistance. Next is density log. The density log determines the electron density of a formation by releasing gamma rays from a source. A detector measures the number of gamma rays that returns, allowing for the determination of the formation bulk density. The litho density tool (LDT) also features a photoelectron cross-section curve for additional lithology indication. Formation bulk density affected by fluids and porosity, in which log recording needed for anomalies in the borehole, and the formation of bulk density influenced by fluid porosity and also metric density. Lastly, neutron porosity log. The concentration of hydrogen in a formation is primarily determined by the neutron log, which is a non-contact neutron source. The highest energy loss occur when released neutron hit hydrogen atom, as they have the same mass. This energy loss is linked to porosity in porous formation. Where hydrogen concentration is higher, the gas filled reservoir may have a lower porosity. So, neutron log interpretation, it is influenced by lithology, porosity, fluid type, and the tool types. Neutron porosity use specific charts like SNP or CNL, and it also directly read log value for the porosity. Um, it is used appropriate chart in log interpretation Chabuk for sandstone or dolomite evaluation. Next, the log analysis and interpretation. Based on the log uh, result, there are three tracks, which the first track shows spontaneous potential SP and gamma ray log. The second track shows resistivity log, and the third track of log analysis show density log and neutron porosity log.
Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Muhammad Afif Ilmi. I'm going to explain how the spontaneous potential SP log and the resistivity log is going to determine the hydrocarbon zone. So for the first one is spontaneous potential. The measurement of SP measures the naturally occurring electrical potential difference between the borehole fluid, which is drilling mud, and the formation water. The hydrocarbon influence be less conductive than water cause a change in the electrical potential. This change is recorded on the SP log, which is an indicator for the hydrocarbon zone. The deflection significance. An upward deflection in SP curve at particular depth is indicative of potential hydrocarbon presence. This is because the electrochemical properties of hydrocarbon alter the SP response. The second one is resistivity log. The measurement of the resistivity logging measure how resistant a formation is to the flow of electrical current. It provides information about the formation ability to conduct electricity, which is why the hydrocarbon characteristic is generally have high resistivity, meaning they are poor conductors of electricity, while formation water is more conductive. So the resistivity can differ between the hydrocarbon and water in the formation. The next one is resistivity increase. An increase in resistivity on the log suggests the possibility of hydrocarbon. This is because of the interaction of hydrocarbons tends to displace the conductive water in the formation, leading to the higher resistivity. In summary, both of SP log and resistivity log are used to identify hydrocarbon zone through the analysis of electrical properties. The SP log look at the natural potential difference, while the resistivity log focus on the resistance to electrical current flow. Combining the information from this log help geologists and petrophysicists make more informed assessment of subsurface formation in the term of potential hydrocarbon present. By using the SP log, we can also determine the lithology of the formation and then define the bed boundaries, which we can locate the depth range of the hydrocarbon located in the well. To define the bed boundaries, changes in lithology often lead to the variation in the SP log by analyzing these changes in SP log. For example, the high resistivity and less SP mean salt water, and high spontaneous potential and low resistivity mean it's contain shale, and the low SP and high resistivity mean sand. So by using the information that we can get from the SP log and resistivity, we can determine the depth range of the hydrocarbon zone.
I'm going to continue the presentation with the analysis of density log and neutron porosity log. For the third track of the log interpretation, we have density log and neutron porosity log. Based on the log, we can identify four zones of hydrocarbon, which we already highlighted on the picture with green color, which there are HC1, HC2, HC3, and HC4. The first hydrocarbon that has been identified was at the depth of 3,850 meter to 3,864 meter. The first hydrocarbon found possibly containing gas and oil, which at the depth of 3,850 until 3,860 meter depth, we can identify that there might be gas exists at the zone. For the depth of 3,861 until 3,864, there might be oil exists at the zone. So neutron porosity line graph curve shift to the right, which indicates less porous zone. The second hydrocarbon zone, HC2, found at the depth of 3,901 until 3,908 meter depth. As for the third hydrocarbon zone, detected at the depth of 3,917 until 3,918 meter. For the second and the third hydrocarbon zone, we suspected that there might be a brine water exist. As for the last zone, the fourth one, HC4, at the depth of 3,932 meter until 3,935 meter, we might found gas existent at the depth. Thank you.
For the result, for the probable hydrocarbon bearing zone with top and base depth, we got for hydrocarbon bearing zone 1 with top 3,850 meter and base 3,864 meter. For hydrocarbon 2, we got top for 3,901.1 meter and base 3,908.9 meter. And for hydrocarbon 3, for the top is 3,917.2 meter and base 3,918.9 meter. And lastly, for the hydrocarbon bearing zone 4, with top of 3,922 meter and base 3,925 meter. So for the level of certainty, we use net to gross formula to calculate the probability of the well. With our reservoir have gross thickness 100 meter and net pay thickness to 26.5 meter. We divided net pay thickness and gross thickness and get 0.265. So the possible of this well is 26.5%. In summary, using a set of log including SP, resistivity, density, and neutron porosity or density, we have effectively detected and mapped hydrocarbon-bearing reservoir in the analyzed depth ranges. Our approach, integrating this log, has proven reliable for identifying the top and base depth of potential hydrocarbon reservoir. The integrated log analysis has demonstrated significant capability in detecting reservoir. By examining changes in resistivity, variation in density, neutron porosity, and density separation, and SP deflection, we have successfully identified fluid filled zone and hydrocarbon-bearing interval, allowing for confident mapping of reservoir depth. Limitation in this analysis stem from uncertainties, including variation in geological formation and potential data quality issues such as logging tool accuracy. Additionally, assumptions made during log interpretation may introduce uncertainty in identifying reservoir. In terms of recommendation, we highlight two important aspects. First, consider acquiring additional data, such as advanced well logs or seismic data, to enhance the existing dataset and better understand subsurface geology. Second, conduct further testing, including well testing or sampling, to validate log interpretation and confirm the presence of hydrocarbon in identified reservoir zone. That's all from us. Thank you.